Well, it's the, there's also a little bit of complication getting when you do the non-factorized form, that's also true. You're supposed to take the derivative.
Are you able to like without?
The entire suite.
That was all cool.
Hi everybody. Sorry to be late. All right. This is the first time that this class has been in this room, and it's kind of a cool room, but kind of weird too, right? Because it's like neither the math nor the CS or engineering buildings, and so one of the things about it too is that there's not exactly like great nearby parking. So for someone like me who has to get here, sometimes finding parking can be a little tricky, but anyways. Thanks to the TAs for having everything set up here, appreciate it. Okay, questions before we get started? Yeah.
So on the audience inputs to the
Sorry, are you talking about the homework?
Yes.
Yeah.
It gives us a list with 2 entries in it. Should we go over all of them?
Right. It's giving you a range of like to kind of to look over. Yeah, exactly. Good. Other questions? All right. We better get started because we're late. Okay, so today we're going to talk about activation functions. These are those nonlinear functions that are going to be between our linear layers. So neural networks are in a kind of general sense of, or just a general description. There are a bunch of layers of linear functions. I mean, it says linear classification, but really just linear functions. And then, if we were just to stack a bunch of linear functions together, we would just have the composition of many linear functions. And then, what would be the outcome of the composition of many linear functions? What kind of function would that be?
Linear.
Yeah, it's linear. You can think of it as like a factorized. It's like, your linear function is a matrix, times your input plus possibly a constant, right? And so when you do this this composition of these linear functions, you get you multiply all those matrices from each of those linear functions, and so you can think of that as like a factorization of a matrix into these kind of like one matrix at every layer. But still, it's going to be a a linear function. And that's, I guess, kind of interesting to observe. There are linear things in this world, but not too many interesting ones. And if you've done anything like, if you've been studying physics or engineering or something like that, you see that many problems actually are nonlinear. Many of the interesting problems. And you use linearity to look at behaviors kind of nearby certain interesting points in your space and whatever. But linear is not enough really to kind of capture the kinds of crazy things we want to do. If you think about the basic example that we've been working on here, classifying an object in image, this is a really nonlinear function of the pixels, the inputs to these classifiers, right? To be able to go from all those arrangements of numbers that represent the intensities of your pixels in 3 color channels to say this is there's a cat here or a dog here or so forth. That's a really nonlinear function. So we want to be able to start with neural networks that represent a large family of nonlinear functions, and then in supervised learning, which is the majority of what we're focused on in the beginning of this class, in supervised learning, where we're trying to associate labels with our data, with our input, you can think of that as like we're approximating some function from the inputs to the outputs, and you want that function or something very close to it to be in that family of functions that you're using, that you're like optimizing the problem on. And so the way that this happens with neural networks is that we have these very simple layers, and then we have in between the layers activation functions, which are typically nonlinear, and they're typically very simple. And so you have a linear layer, you have then a nonlinearity, so a simple linear function, simple nonlinearity. And you might think, well, that's not very complex. Maybe maybe the nonlinear phenomena that I'm interested in modeling will not be captured in that, and that's probably true. However, as we stack these things up, linear, nonlinear, linear, nonlinear, even though each of those is relatively simple, the composition of those all the way throughout and having this depth actually can be can give you very complex behavior. And that's kind of one of the reasons why modern neural networks are working. Now, at the end of this lecture, we're going to talk about something called the universal approximation theorem, which will tell you something about how, like, the family of neural networks with a single hidden layer, and how well those approximate like certain kinds of functions. So we'll talk more about that at the end, but right now we're just going to focus on activation functions for a little bit. Like, what are the typical activation functions that you will run into and that you will use in your own neural networks, or you'll read about in papers about modern neural networks. So here is a list of some of these that you will run into. We're going to go through kind of each of these and talk about the pluses and minuses. Pretty much these days, ReLU is the standard, or some variant of that. Sometimes you might see leaky ReLU. Sometimes you might see an ALU, just an ELU here, or these days there's things like GLUs, but they're all these LUs. And the LU part of this is well, in ReLU it's a rectified linear unit, and the idea is that there's always some sort of linear component of this. So this is the linear component in ReLU. Here it is here in leaky ReLU. Here it is here in the ALU. And the GLU is kind of the same thing. There's always this linear component, and then there's something else happening. So these are typically linear when x is greater than 0, and then there's something else happening when when where your input is less than 0. But this will give you kind of a flavor of how to think about what these are and what behaviors you might expect from them. But in general, tried and true, this is by far the most common activation function that you'll run across in kind of common modern neural networks. Okay, however, sort of things started off in neural networks and persisted for a long time with the sigmoid activation function, that top one there. And as you look at these ones, it's kind of interesting to, we'll dive into the specifics of that, but kind of interesting to look at that compared to the rest of these here. By the way, this max out is, I don't have a picture of it here because it's got too many parameters in it, but you're basically combining two linear functions, and whichever one's greater. So it's got it's got linear behavior to it, but it's got kind of two lines that are crisscrossing, and one of them's going to be larger than the other, depending on where they intersect and what the slopes are. Okay, so let's talk about the first and famous, maybe now infamous activation function, sigmoid. Okay, so you might have run across this before. Well, in fact, in our lecture from last time, we actually were looking at the computation graph for a sigmoid, and we thought of this as like a single gate or node in our computation graph. And it looks like this. It looks like this. Plotted over here. It's got some interesting properties, and we'll talk in just a second about, well, we'll talk about it here, about why it was chosen kind of first off. But in particular, what is this doing? Well, this is taking, whatever our output might be from the previous layer, which now becomes the input to this activation function. And in general, there's no restrictions on what that might be, other than it just needs to be some kind of real number. And remember, we are often applying these activation functions in an entry-wise way. This sigmoid might be applied to each of the outputs from your previous layer, right? So this is a linear layer, it's taking from n inputs to n outputs. Then you'd apply this to each of the n outputs individually. Okay. And it has one really nice property, which is it squashes everything into a particular range. In this case, from 0 to 1. So it takes your arbitrary output that could be kind of any real number, and it squashes it into a range from 0 to 1. Now, why is that good? Well, there are some interesting properties of that. There's like some ways of thinking about that as like, giving you some kind of score on a scale that you can understand. You can think of this as like a probability, right? Like, if we take whatever is our real numbered score and we squash it between 0 and 1, that squash, that output, can be thought of as like a probability or a likelihood of a thing occurring. And beyond that, one of the, well, probably the reason why when people started thinking about neural networks, first off, they were thinking about these as like approximations to what we see in the brain, right? A bunch of neurons connected together, and the output of one neuron sort of affecting the input, or becoming the input to another neuron and affecting what happens there. And if you squash these things on a range like this, you can think of this as like a firing rate or a proportion of like the total output you could get from this neuron, as something, as something between 0 and 1. You could scale that. You can multiply it by some other value to give you maybe something like a firing rate. But anyways, it's just it seemed convenient and a good idea at the time when people were like, hey, brains are, oops, I thought there's a picture coming, but it's not just yet. Hey, brains do this kind of thing, so let's try to model what's going on with the brain. Okay, so turns out there are a bunch of problems with this kind of activation function. And what I want you to think about is the fact that what we're trying to do is we're trying to propagate like error signal given to us by the loss, all the way back through from the output of your network, that's the loss, or the measurement of how the output is performing, all the way back through your network, so that you can adjust each of the weights along the way, right? Like each of your layers, each of your linear layers is going to have its own weights, and so you want that error signal to be propagated back through the layers using the algorithm like backpropagation, or the algorithm backpropagation to do it. And so we're calculating gradients along the way, and you're passing downstream gradients upstream through chain rules with this product, and you just keep going. So there are some problems with this kind of activation function, and I sort of already showed it. And if you're looking at the slides, you already can see it as well. But what are they? There's sort of three major ones. What are they when thinking about the fact that you need to propagate signal? Does this kind of activation function help you propagate signal back upstream? Thoughts on that? Ideas? Remember, we're using gradients as a way of as the signal, right? So the changes of the final loss with respect to parameters. So how might this make that a difficult thing to do? Yeah. So that's like the most important one. Is that in this range near zero input, I have basically a linear function. You can do your Taylor expansion about zero and see what the slope is there. You can even have weights for this activation, although that's not typical. You think of just like the layer coming in, so just providing those weights. So you have kind of linear behavior here, and that's good, right? Like that gives you a nice clean gradient, just a slope there. But as soon as you get away from zero, that slope starts to, in either direction, that slope starts to approach zero. In fact, it approaches it pretty quickly. You can see, just from this plot here. So the slope being zero is problematic, right? Because that means that the gradient of this activation function, when you're away from zero input, is zero. And remember we talked about this last time. We were thinking about like different kinds of gates and stuff. If you have zero gradient or a very small gradient, what happens as you start to do backpropagation and pass that information upstream?
Everything upstream from that point doesn't contribute.
Exactly. You're multiplying by this very small gradient. It's a small number, so it's making everything else small. Now, it could be possible that like there's another gradient in that product that's like really big and it balances out, but in general, this saturation, this squashing, this saturation of the output to be between 0 and 1 is killing the gradients. It's setting it to 0. And then that means that, as you go upstream from that, everything else upstream has really no possibility of affecting what's going on, right? And that's kind of an interesting thing to kind of just get used to is that, even though the output here might be non-zero, right? Like if you're way over here, the output might be 1. It's the gradients that we care about. So it's not just the output value, but it's the gradient at that value. So that's really problematic. If you want to use gradients as signal to update your weights, to train these models to find better weights, then having 0 gradients is a problem. So if you could guarantee that everything sort of stays near 0, within this linear range, you'd be good. But you can imagine that's a pretty hard thing to guarantee.
So you might get to this in a second, but the ReLU function, anything less than 0 has a slope.
Yeah, we will cover this in a second.
Okay.
So it has some. There's some related problems there as well, but we'll get to that. Yeah, and good noticing and making that comparison there. Okay, what other problems might there be here? For those not looking at the slides, think about what we're trying to do here. Try to pass information. This is just a nonlinearity between linear layers. thoughts?
The output is between 0 and 1.
Okay.
And maybe we have negative. We should have negative output.
Okay, yeah, so there's something really interesting about this, that like the output itself is between 0 and 1. Remember, the output is not yeah, hold on, let me think about this for a second. Yeah, that is problematic actually. So what's problematic about that? What's your thought on that?
Maybe one of the features have negative impact the output of our classification problem.
Yeah.
Something like that.
Yeah, think about what this is doing, right? You have this like linear function. It can kind of map you anywhere, you know, like each individual value to anywhere on the real line, because it's just like this. It's linear. But now you made it basically a positive value between 0 and 1. So you took like, if you think of this as a mapping from one space to another, you took like the whole real line and you mapped it into this small interval. So perhaps you're like, and not only that, everything has the same sign at that point, right? Everything's positive. So yeah, that can be problematic, but maybe like the reason why is kind of a little bit tricky to see. No, sorry. Next. Oh, gosh, I don't even have that. Well, okay. So this is another way of wording that same problem. It's not zero-centered. It's actually the fact zero-centered meaning that like, you know, we have like as many negative values as there are positive values, or like some balance in terms of the measure of those. So it's sort of it's something very similar. So what's the problem here? This actually is not, I don't think is like super obvious or like, you know, very intuitive, but it does make for poor optimization. So it's not like the end of the world that there's like that everything gets mapped into this kind of like positive cube, so to speak, but it does make for weird optimizations at times. And here's the idea. So let's think about this when like, let's think about these linear units when everything is, when all your input is always positive, okay? So remember what we're doing. We're taking gradients with respect to the parameters, which are W in this case. So when these are linear. So what happens when I take that gradient with respect to W? What am I left with? I'm left with this. I'm left with my data point here, right? Or like, you know, the input. Well, that input's going to be positive. So my gradient is going to be positive. In fact, as I do this, you know, for all of the weights, everything's going to be positive. So what does that say about my gradients? They're all kind of, they're sort of restricted to, you know, like what we would call like the positive cone in some sense. Actually, it's this cube, but it's the gradients are restricted to either being all positive or, you know, given something about, you know, where we are in terms of nonlinearity. There could be, when we do these gradients, there could be a minus sign applied, and so they'd all be negative. So I think this is coming up next, yeah. So our gradients are either pointed kind of, you know, this is only in 2 dimensions. You can think of this in n dimensions, as we often call this as, you know, the positive cone or negative cone, where the steps you can take have to exist in this cone. But let's say that for the optimization, you know, the optimal parameters are like somewhere over here, meaning like the step we want to take is not in these cones, but the step is like in, you know, some other direction. We can't take that step. What we can do, or the only thing we can do, is to take zigzag steps in the sense of, you know, we can choose, you know, gradient steps along, but we don't get to choose them. But the optimal steps would be along these boundaries of this cone, and so we would be taking steps sort of in a zigzag pattern to go down this diagonal, so to speak. So it's weird for optimization in this case. Now, if the direction we need to go to like get to optimal weights is here, then things are fine. We can actually you know, quickly find that. But if we need to do this, then we have to take kind of weird steps. So that's actually, it's kind of subtle and kind of a weird, maybe not intuitive, thing that happens with these sigmoids, but it is as a thing, and it's something that you can kind of play around with and see for yourself. Remember, so what was the issue here was, well, when we take these gradients, when we do these, like we do this chain rule with f, the output that comes over here is the gradient of this term with respect to, say, wi, right? So we're left with the xi. So if they're all positive, or they're either here, or if, again, like the term that comes out of here ends up being negative, then we have negative tangent. So it's all here. So you have this weird behavior. Now, in general, that's because of what the value of this input is, x1. Now, we're not quite there yet, but one of the things you're going to see when we think about the activation function, these nonlinearities that we put in between the linear layers, is we are going to have these kind of ReLU behaviors. It's going to give us some similar behavior, some similar types of behavior. However, we're going to add another nonlinearities that are going to enforce our data to have a kind of zero mean, or at least allow for there to be zero mean. So like a way to shift. So even if this does happen, a way to like learn some parameters to shift. And these are things known as like batch normalization, and we'll get there. We're not quite there yet in terms of lectures, but we'll get there. And it's one of the reasons that it exists is to do this, and there are other reasons as well. But again, we want to pay attention to the signs or values of this because they end up being proportional to the gradients. Okay, there is any questions on that? It's a little bit of a weird, subtle point.
Why do we need zero mean data?
So zero mean data would mean that we would have both positive and negative values, right? I mean, everything could be zero. That would also have zero mean, but in general, you don't have that. So if you have zero mean, you're going to have some positive values and some negative values, and that's good. That gives you a range in which to kind of, that gives you better steps that you could take when optimizing, walking down your loss function. Good. Yeah.
So this graph here is
this one right here.
2 dimensions, so it's like
Right.
It's like vector of x1 and x2.
Right.
Okay. And
Yep.
then we can only go in.
Yeah, but in general, this will be in n dimensions. But
This is simplification.
yeah, simplification. But the same thing applies. Think about a third direction. This would, there's like this positive cone where all of your inputs have to be positive, or all of your inputs. The negative cone would be all your inputs have to be
That's
negative.
how we calculate the gradient.
Yeah.
The gradient of both the x1
Yeah.
and x2 have to be both positive.
Yeah, if our activations are making everything positive like the sigmoid does, then this kind of thing can happen because the output from your previous layer becomes the input to your next. Okay, I think there's another question.
So, sorry, this might be simple, but I'm having a hard time understanding what you're saying about how it can be either all positive or all negative. Because if we're applying the sigmoid, doesn't that force everything to be positive no matter what?
Right, but then what we're doing is we're computing gradients. So then there's going to be a chain rule here with this outer function and the inner function, like our linear layer and then our nonlinear layer. So the linear layer is going to give us a contribution of just positive gradients, and then the outer layer is just we'll just like scale that by a scalar in general.
Okay.
So either going to be it'll be like a positive or a negative. So it'll make so the final gradient will either be all positive or all negative.
Okay, I was thinking about the time.
Yeah. Just that simple composition. Yeah.
So is it like each bidder was one step, and that's why the last step we can actually, because we're going negative and negative?
Yeah, exactly. Yeah, you got it exactly. So, we finally took all these steps. You can see like there's a kind of, the reason these are all the same size, like maybe you've used the same learning rate or whatever, but then, yeah, this one we can step towards here because that is a vector that is in the negative cone. Good. Okay, so this is just like remember in a couple of weeks when or maybe it's next week, I think it's maybe next week, when we start thinking a little bit harder about how to craft these neural networks so that they train easier. I mean, there's a lot of reasons why we're using neural networks today because a couple decades ago, you basically were like you were thought to be like a complete like crack if you were using neural networks to do machine learning. That like it was basically you couldn't write grants or anything like that for doing neural network research. It was just neural networks were thought to just not work. Like there were some theoretical reasons why they might work, but people couldn't make them work. And so people figured out there was just a number of innovations along the way. Some of them, innovations in hardware, like the use of GPUs to speed things up. Others were like improvements in the architectures. And so one of those is to move away from sigmoid activations to other activations, and we'll talk about ReLUs and like why they're great. But like other things happened as well, like some of the other activations that were happening that allowed, like basically, improved the dynamics of your gradient descent. So there's like a number of different flavors of stochastic gradient descent, and some of which really speed this up. So it's just like it's a computational speed up. Like you've improved rather than just taking some goofy steps like this. You switch up your activation functions. You make sure that you've got zero mean data, and now you can train really deep networks all of a sudden, and that changes everything.
So was the sigmoid part of the loss function or part of the initial?
Okay, this is a great question, and you may not be asking it for the reason I'm going to answer, but I'm going to use this question to answer to give an answer. Then you tell me if you still have a question. Okay, so we're talking about this as an activation function, so a way of introducing a nonlinearity between linear layers. Okay. However, a sigmoid often shows up as not a loss function, but as the final activation. If you are, say, doing like a binary classification problem, because it actually is giving you a single value between 0 and 1, so you can interpret it as a probability, and it can be the probability of like the object being in your positive class, and then 1 minus that is the probability of your object being in the negative class. That's why I'm restricting it to binary classification. And then you can think of this as like you can have multi-class classification where you're doing this for each of these, in the sense of multi-class in the sense that there's maybe multiple classes of things within my object that I want to call, not just one, but multiple of them. So these things show up as activation functions because they're just nonlinearities. But they also show up in the final activations for certain kinds of tasks, because they give you the kind of like output you would want, that you then pass into a loss function to measure like how well you're doing, right? So like in a binary classification, you're going to compare the output, like that probability, with say a 0 or a 1, depending on which class you're in, and then you're gonna use the difference there as a signal that you're gonna backpropagate through and change the weight, so that for positive classes that outputs a 1, and for negative classes that outputs a 0. So I know that wasn't exactly your question, but you still have a question?
I think I figured it out, because I forgot that when you do the loss function, you're actually using the linear classifier, or not in this case, non-linear classifier, using the results from that in your loss function.
Right. Yeah. So like there's one more function that is your loss function on top of like the actual architecture that you're working with, and that last layer needs to kind of give you something appropriate for the loss function. It needs to give you a class of number that it can use. In a case of like binary classification, you would use something like binary cross entropy, which is the loss function, and that needs a probability, a value between 0 and 1 to compare with. All right, cool. Great questions. Okay, there's one more we haven't talked about. Maybe not very obvious, but this exponential can be expensive to compute. I mean, it's actually in like really like modern hardware. Maybe it doesn't matter for like small networks or small data sets, but I think this can matter for larger data sets. But this is a weird thing. How do you implement it? How to compute that numerically? often this is done via some other kind of approximation, some kind of truncation of a series, or other, depending on the size of X, some other kind of known, approximations or whatever, for functions that are easier to compute. So there's some expense associated with having to compute exponentials of things. And so since you're going to do a ton of this, right, you're going to have, like, if this is the activation function that you choose, and you're going to apply this to all of, each of the outputs individually for all the outputs in all your layers, like this can become, you're going to do a lot of this at every single batch, right, every single iteration of your learning. And so that expense could add up and make it so that, I don't know, your training is 20% longer, 50% longer, I don't know, it kind of depends on what's going on, but there's that as well. Okay, so in general, we don't use sigmoids as activation functions. We found better things. It's not like they don't show up every once in a while for like really good reasons, especially as like the final activation in a network to give you an appropriate value for a loss. But they generally don't show up. And you can kind of like, you can, like, if you see somebody using a sigmoid, you can kind of look at them and say, you're new at this, aren't you? Yeah. Let me tell you all the reasons why you shouldn't do that. Okay, so what other things were tried? Well, the next thing that started to show up were these hyperbolic tangents. Why hyperbolic tangents? Well, they still have the squashing. They still have the squashing behavior, which again was thought to be, good for certain reasons. But this now is an odd function about 0, so it's kind of got this nice symmetry, and that's going to at least overcome the weird stepping behavior that the sigmoids would give you. And so that's good. Centered is good for that reason. You can get both positives and negatives, but we still have the saturating behavior, and so this really limits you in training deep networks. So you can't train very deep networks, and so papers that were coming out at this time, like some of the first convolutional networks, were using Tanch, and the networks aren't very deep, and you couldn't go much deeper than a couple of convolutional layers as a result. But it solves some of the other problems, so great. So sometimes you still see Tanches around, like in odd places. And if you ever see a sigmoid or a Tanch, you really should just like stop and say, why is that there? Because there might be a really good reason in a particular architecture for like a particular activation to be chosen that way. Usually having to do with the range that this gets squashed into. But in general, if it's a bad choice. And like if at the final project, if you're building your own network to do a thing, and you have like Tanches or sigmoids, I'll know you didn't listen to this lecture. And you didn't catch one of the most important things. No. I don't know if it's the most important thing, but it's really quite important. All right. Questions about Tanch? Hyperbolic tangents. See, did you ever, when you took your whatever class that you were taking, I don't know if it was geometry or calculus, and you might have like had that thought in your mind, will I ever use a hyperbolic tangent ever? Like, somebody did. For something not for for something kind of really unusual for its properties, but I don't know. They show up. Oh, there's also one more thing in here, by the way, that's not being said. That's also problematic with Tanch. It has to do with the cost of computation. What is a Tanch?
Exponential.
Yeah, it's a ratio of exponentials, right? So there you go. Also, you got that problem. Okay. Then all of a sudden, we get to 2012. Now these were being used before here, but like this is the paper. This is the paper associated with the group that won in 2012 the ImageNet classification competition. That really kind of started like the deep learning revolution. And this is really like the first paper to like use ReLU, and ReLU really made a difference in the results. There is a convolutional neural network in this paper called AlexNet, and we're gonna, in a couple of weeks, we're gonna work through kind of the history of the ImageNet classification as a way of thinking about the development of neural networks, modern neural networks, and in particular convolutional networks. But this is like ReLU's become really popular here because they clearly were a major component of how this team was able to win. By the way, the three authors here, Alex, Ilya, and Jeff Hinton, went on to form a company of just the three of them and sold it to Google for $44 million. So maybe ReLU also made them $44 million. I don't know. But you think, is that activation function worth $44 million? Well, they did more than just the activation function, but it's a really simple function, right? Very, very simple. It's simply this max between the input and 0. So if you think of a single input, when your input is greater than 0, you're just x. You're just this like line with slope 1. And then if you're less than 0, you are just 0. Okay? So what's good about this? Well, it's already on here. Well, let's talk through this now that we talked about some of what was wrong with sigmoid and tanh. So, at least in the positive region, it doesn't saturate. Instead of having like a very narrow region where you have this kind of linear behavior, which is good. This is very like efficient, signal to propagate when you're thinking about gradients. It now has the entire, positive half of the real numbers as a linear range. So now you've got a huge range of numbers to work with, where you have, like kind of this linear game. Turns out that's fantastic, and it's sort of weird if you think about it, right? Because remember what we're trying to do is that we're trying to add in nonlinearities between linear layers. This is like maybe the most linear nonlinearity you could kind of think of, right? Like it's linear, it's like piecewise linear, and it's piecewise linear. That's it. So I think that's kind of weird if you think about it, right? Like I just spent I don't know how many minutes telling you about how we're trying to come up with this like family, like these neural networks to represent the family of all these nonlinear functions that you could want to be able to find in your optimization during optimization to approximate the actual function of, say, going from images to classifying what's in them. And these become like a really, really important part of that, and yet they're very linear. So yeah, like it's not clear that this should work. In fact, it took forever, if you think about it, like in the 80s and earlier, way back to the beginnings in like the 50s and 60s, when people were starting to write down perceptrons, like the very first kind of neural network architectures, they were using activation or sigmoid activations. Like it was thought that was really, really important. And then you get to tanches, which kind of fix things, but it's decades later that you finally get ReLU. So like, why? I don't really have a good answer for this other than the ReLUs allow you to have depth, and depth is really, really important for representing lots of different kinds of nonlinear functions. And these just are very efficient in terms of providing a kind of nonlinearity, enough of a nonlinearity so that when you compose these with many layers, that you get enough, you get lots of nonlinear behavior, and yet they're very efficient because they're basically linear. So don't blame the machine learning scientists, up to this point for only discovering ReLUs 10 years ago, or a little bit more than that. Like it's sort of weird that these are the things to use. In fact, can't remember what the quote is, but Jeff Hinton himself like says something about like these really shouldn't work, and yet in practice they do, and so there you go. So they don't saturate. You have this huge linear response. They're very efficient. Why are these very efficient?
One comparison.
What's that?
It's like if your input's greater than 0,
Yeah.
output your input, otherwise 0.
Yeah. So very simple comparison, and a comparison with a value 0, which is like somewhat easy to compare to, you know, on a like in some whatever bit range you're looking at, and it's just itself. So like if you just do this one comparison, and then you can just use that value. You've already got it out of the register because you did the comparison. Like you can just like, there's your output, blop. It's like you don't have to compute anything else. It's just got that one comparison. And if it's not that, you just have a simple constant 0 that to output. So it's really efficient. There's no exponentials in there, and there's no like. It's just one comparison to execute to get the output of this function. So super computationally efficient. And yeah, turns out that even though there's like, if your value is negative, you lose the gradient entirely here. Even though that's the case, it turns out that like your models will converge way faster when using these activations than using these other ones that we just looked at, sigmoid and tanh. I don't know. This number is just a number. Are you impressed by 6x? I don't know. Could be 100x. I mean, it's just way faster. So why is that? You were asking this question earlier. Why is that? Why does this work? Why do you think it works?
You like disregard things that kind of don't matter that are in the 0 range, and then you amplify things that do matter in the positive range.
Yeah. So there's a really simple kind of decision happening here, right? It's like if this input to this part of the layer is going to be useful for the final task, then we just need to get it somewhere into the positive range. We just need to get it somewhere. And if it's not, then we just need to get it somewhere in the negative range. And remember, when you're updating your weights, every time you update, so yes, during that update, you've kind of killed anything upstream of a negative output here, contributing to the loss. But as you change the parameters, you're giving those inputs again an opportunity to contribute. And it might be so negative that they never, you never iterate your weights enough for that to become positive. But in general, we initialize things so that like we're basically starting off kind of near this critical point, and then this is actually another important aspect of getting networks to train well, is how we initialize the weights, especially during this period. There's actually like now innovations that kind of make that less important, but it's still important. And we sort of start off there, and we sort of let it work itself out. Like there's a bit of randomness as we kind of start in terms of what should be positive, negative, but then we kind of get into some nice range, and then we're finding our way to our local minimum. So yeah, so like it's like an easy decision that it's kind of like a parsimonious decision that these activations are having to make. Like either this is contributing or it's not. And so yeah, lots of saturation of gradients, but you have a monstrous range in which to put things if they're going to contribute, which is is like the major reason why this works. Now it also has the problem that we talked about of everything being mapped to, like all the outputs being mapped to positive values, and we need to overcome that still, but we overcome that in a different way than say zero-centered MDs. So that's still a problem here, but we're going to overcome it in a different way. Okay, questions about this? Do you feel surprised? I mean, I don't know. Like when you're first learning about this, you might go, "Who cares? Like if it works, it works." But like after a while, you might look at it and be like me, and you're like, "That is so weird that works," and it works super well. And like the question is like, what's the next innovation to that'll work even better? Yeah.
I'm trying to think of a metaphor for how, like, again, a linear integration function could, combine with other linear things, give out like a non-linear thing. So at least the metaphor I can think of, I'm not sure, tell me if it's wrong. Is it like drawing multiple smaller lines to form like this circle? Because ultimately you have like a non-linear shape, but it's made of lines. So is that kind of what's happening here in like higher dimensions?
I mean, let's think about that. In a way, yeah. In a way, yes. Like, in a way, what you're doing is you're kind of carving out, like at each layer, like a part of space that's going to contribute and that's not going to. So there's a kind of boundary that's being chosen there, and it's not really like you're creating this kind of convex shape in that way, but yeah, like all these things are coming together to kind of form the boundary between what contributes and what doesn't, and yeah. So yes, actually, there's as weird as it might seem, there's a really interesting final project in that question, and like thinking about the geometry of these ReLUs, and there's like been stuff written on it, and so it's kind of a fun thing to read about and understand better. But there's probably lots of ways you can simply extend that and have learn a lot about the question that you just asked, but then maybe contribute in some small or large way. Yeah, not 0 cent anyway. I should have already clicked through this. Right, I'm not following my slides very well. Hey, yeah, we have active ReLUs and we have dead ReLUs. But that's okay. So I mentioned this earlier. So how do what's one of the ways that we sort of deal with this? And the way that you deal with this is that you choose your weights in such a way. So remember, when you start training, you're going to have to sort of the typical way to start here is to randomly initialize your weights. When using ReLU networks, you want to choose those weights in a way that the average activation is just slightly positive. So in general, there's you're getting some response, but you don't want it to be too large and really bias yourself to be way over in the positive range. You kind of want to be near this kind of critical point of 0, but you want to be positive so that there's some signal so that you can quickly kind of update things there. And we're actually going to talk about initialization here real soon, I think next week. Anyway, if it's not next week, it's the next week. And if it's not that, it's the week after. I can't remember right now. But it's coming, I promise. Okay, great. So one of the things that you ought to be thinking right now is, okay, well that's all good, but why should I put up with there being no gradient when the value's 0? Why not? I want a nonlinear function, so I can't just have x. Well, why not just have another linear function there that doesn't have slope 0, that has some other slope? And that gets you into the world of other kinds of ReLUs. And maybe the simplest one to think about here is what's known as the leaky ReLU. So it's basically it's the match now not of 0. You can think of, there's a slope here that's like a parameter, and for the ReLU, this slope was 0. But now we have something that has a very small slope, 0.01. So compared to 1, this is 100th of that. So a very different slope, but it's not 0, right? So, and we're taking the max of this, so you think there's 2 lines here, and at 0 they cross each other. And this, when x is negative, this is the larger value, and when x is positive, this is the larger value. Okay? So this is what's known as a leaky ReLU, and it's called leaky because when x is negative, it's like leaking a little bit of signal there. Some clever person named it. So what's good about this? Well, yeah.
Gives it a chance to recover.
Yeah, now you actually have learning in the negative range as well. It's at a different rate, and notice that we've chosen it here, like this is a very typical choice of a leaky railer, that to be 100th of, the slope to be 100th of the positive one. So there's like, you know, the contribution to the gradient is 100th for a negative point, or negative input as it is for a positive input of the same absolute value. What's that?
Stay positive.
Yeah. Right. So this there is a bias towards positive, and again, this has to be nonlinear. So you still, you know, it still is just this piecewise linear thing. So what this is doing is again biasing you to being in the positive range when that signal is important for you know, determining, like for performing your task as determined by the loss. So, you know, it has all the same benefits as the ReLU, except that it doesn't saturate anywhere. Still efficient. Again, you're going to converge much faster, and you know there's no saturation. You know, it doesn't die. Right? The gradient doesn't go away. So weirdly, though, you don't see these as often as you see ReLUs. I don't really have a good answer for that, other than just like ReLUs work, and they sort of work as well, or maybe even better than these. Like they actually are slightly more, you know, computationally efficient. So maybe that has something to do with it. But even though these like maybe appear to have you know, some advantage over ReLUs, it doesn't mean that like now everybody's using leaky ReLUs. It just is like, I don't know. It just doesn't. It isn't a thing. And like, there's maybe a reason you can think about it. I never really, you know, I never really gotten this deeply to look at it myself. But you know, even though there's a bias towards positive values, like this could also create a bias towards very, very negative values, and that could be kind of weird. Like your initialization probably will prevent you from ever seeing that, but I guess that could be weird. And maybe there's some other things, but even though these might look like they have, you know, they're better than a ReLU, you don't often see them, or you more often just see ReLUs. Questions about that? This is another winner of the ImageNet competition in 2015, by the way. So did appear to be helpful there. Yeah. So now that you've seen this, you can think, well, I can have this be, you know, I can have this slope be anything. In fact, I could even learn the value of this, right? So if you let this be a learnable parameter, so that you're optimizing this, the slope for the second branch here, this is often called a parametric rectifying linear unit. So this would be a parameter that you'd learn. So instead of fixing it to be 0 or to be 0.01, you backprop through that parameter as well, and you can learn it. Again, you might think, well, that's got to be better. It doesn't turn out to be better. Not typically. In fact, I don't even know an example that where like this is much better, to be honest. What other things are like this? There's the exponential linear units. So you have this kind of behavior when the value of x is negative. And so what's it doing? Well, it's now squashing this signal between 0 and -1 exponentially. So why is that? Why would you even think about doing this as compared to say like the leaky ReLU with a small slope? It does have this behavior that it doesn't give you a bias towards very, very negative, you know, inputs to the activation function. It does have this problem of there's an exponential there, so maybe that's not good. You could approximate this with other kinds of linear, like piecewise linear functions, right? You could allow the range of this to instead of being at 0 where we change the slope, to allowed to go down to -1 when we change the slope, and then maybe a 0, or have like a slope of 0.01 and then a slope of 0, or you could imagine putting all these things together. Turns out that, like, in general, these don't really give you much benefit or any benefit at all over ReLUs. And I think, again, the reason is that you have so many parameters in your linear layers as you're working through this that the network can learn to adapt to ReLU just fine. It's like enough nonlinearity where it can learn just fine. But anyways, there are these things as well. They exist. In general, you could have two just linear functions that you're taking the max of, right? So one of these linear functions would be bad. That wouldn't be a nonlinear activation. But if you put these two together and have a max, then now you have a nonlinear function. It allows you to you think of these as learnable parameters. So it allows you to sort of learn two different lines that might help you optimize the task that you're doing. So these things exist. Again, like you might think, gosh, that's got to be great. That's got to work great. Why, everybody's got to be using those things, right? But again, they don't really. You don't tend to see these. They don't tend to give a benefit over just using ReLUs. And again, like if you're learning these parameters, they're actually very simple parameters to learn, but you are really increasing the number of parameters that you need to learn for each of your outputs, just compared to just learning the linear activation, the linear parameters, and so the parameters from your linear layers. So in practice, you don't see these, but it exists. A smart guy named Ian Goodfellow introduced it, but you don't really see him. So what does this all mean? In practice, basically you're just using ReLUs. You might try some of these other ones out, but you're probably not going to see much happen. The ReLUs will be as good, maybe even better. Who knows? You maybe could use Tanch if you were just feeling kind of like saucy and just wanted to see what would happen, but probably going to be worse than ReLUs. And then just don't use the sigmoid. It's just like so obvious that you don't know what you're doing if you put a sigmoid as an activation function. Again, you could use it as the final activation if that if that gives you an appropriate value for your task, like a binary classification. But otherwise, you wouldn't want to do this. Okay, so that's kind of a brief introduction to activation functions.
Do you know if the sharp corner on ReLU has an effect at all? Because I noticed that the exponent in the other ones kind of give you a curved corner, so the derivative is available.
So, like you might think, yeah, that's a problem, but in general, you pick one of the branches to be your derivative at 0. So usually 0 is assigned a 0 derivative, but you could assign it to be you could assign it to be a derivative of 1 as well, and it wouldn't matter because you are rarely, if ever, actually getting a 0 activation, like a truly 0 activation. It's a single point in a continuum of points, which is not totally true on a computer because you discretize. So it's a single point amongst a very large number, 10 to the 16 or something like that, values you could choose from, and so it rarely happens, and you don't even have to really worry about it. But in general, those are just assigned a slope of 0. I mean, you have to assign it something, otherwise, the program, your network would cough hard at that and stop, and you don't want that to happen. So it doesn't create any problem at all. Okay, so in the few minutes that we have left, let's start putting this all together. So, fully connected neural networks. So, what have we done so far? We've had these linear score functions. Well, let's make a 2-layer neural network. What does a 2-layer neural network look like? It looks like a linear layer for the first layer, then a nonlinearity. Here's a Rayleigh nonlinearity, and then whatever the output of that is, you multiply with another matrix, and that gives you like the output of your second linear layer. And all of a sudden, we now have a 2-layer neural network. Sort of disappointing, huh? Like, neural networks seem so exciting and amazing and powerful, but there's your 2-layer one right there. And of course, you could just keep iterating this and make a third and a fourth, and you could just keep doing these maxes. That would be your nonlinear activation. But yeah, this is like what neural networks look like, and we call this fully connected because what we're doing is with this matrix, we're allowing this matrix to take on all kinds of values between minus infinity and infinity for each of the entries. And so there's not a restriction of like, so if that entry is non-zero, that weight is non-zero, then the input in that column of W1 then has an effect on the output of that row of W1. So it's like connecting entries of your input to entries of your output. Think of it as like a graph. There's like a edge between an entry of the input to an entry of the output, as long as there's a non-zero weight in the correct the correct entry in that matrix. And so this is what's known as a fully connected network. All of the inputs at every layer are connected to all the outputs, or at least potentially can be connected to all the outputs at every layer. This actually tends to be really expensive in general because these matrices can get large very quickly, especially for things like images. We already saw how that can get really large just for small images like 32 by 32 3-channel images. But nevertheless, this is what fully connected is. Now, you've heard talk of convolutional networks. Like the innovation there is that we're going to not going to have fully connected networks. We're going to change the architecture so that we have lots fewer parameters, and yet still able to learn the kinds of things you'd want to learn, like the statistics of images, for instance, or kind of spatial, like locally spatialized, or localized spatial statistics. So anyways, but in general, this is what fully connected layers look like, or fully connected neural networks look like. Yeah. If we go back to our example of CFAR, the CFAR 10 that has 10 classes, remember the input was 32 times 32 times 3. That ended up being, you could stretch it out as a vector of size 3072. And before, we had this matrix here had 3072 columns and then 10 rows, and that gave us the 10 scores for each one, one score for each of the classes. But we have another layer here, so we can choose really any number of hidden units here that we want. Here, this is 100, but you could choose it to be whatever. And now you have a matrix that is 100 by 3072. That's W1, and now you have a matrix W2, which is 10 by 100. And that's it. Now you have a 2-layer neural network. And in between, to get to this H, after you do this matrix multiplication, you're going to apply your nonlinearity. In this case, this Rayleigh, and that will be H. That will be your output. Okay. For the score, we typically on those last layer we don't think of that as having like a nonlinear activation yet until we decide what the loss function will be, and then we apply an appropriate activation there to give you the right kind of value. Like when we were looking at the softmax loss, there was a softmax activation layer here, right? That turned all your scores into a probability distribution. And we're going to be able to learn similar so remember how we had this before, right? So where does this live now? Where does this concept live now? remember each one of these was a row of W. You know, the row corresponding to the class indicated here above. Where does that live now in our multi-layer neural network? What's that?
In the hidden layer.
Sort of, right? You could say plot this somehow, but does this, you know, does the 100 here correspond to an image anymore? It doesn't, right? So you know, you can think, well, I still have 3072 columns here, so maybe W1 could be, we could look at that, and yeah, you could, but you'd have 100 of these to look at, and they would just be kind of, you know, they would correspond to concepts that probably would be hard to associate with any one of these classes. And same thing here, right? There would be something that corresponded to classes, but then the question is like, how do you think about those 100 values? Like, can I visualize those somehow? So the point is that by putting in this hidden layer, I sort of lost this kind of interpretability. Now we're going to get it back by, we're going to, again, somewhere down the road, in a couple of weeks, we'll be thinking about visualizations of convolutional layers. So there'll be a way to think about this at each layer, some really fascinating ways of thinking about this. But in general, we've broken up this idea of being able to just visualize like a prototypical example of our data set per class. So we're kind of giving something away by there being depth here, some kind of interpretability. But that's good because we're gonna gain the ability to actually do these tasks, because this now is going to be able to approximate a much larger set of nonlinear functions, hopefully one of which is, you know, a great function for doing the task at hand. Yeah, we can keep going. What was the question?
Yeah, I had a question about the 100. So you can choose W1 to be whatever size.
Yeah, whatever size. I mean, like, it has to have 3072 columns because your input's going to, your input's a column vector of size 3072.
Yeah.
But it can have whatever, it can have any number of rows that you want. It's kind of like a hyperparameter in some sense. It determines the architecture of your fully connected network. So it could be 100, it could be 1,000, it could be 2, and yeah, then you know, determining what that ought to be for your problem is one of the possible like sets of hyperparameters that you might want to tune when training your networks.
And in general, do you go down in size?
With fully connected layers, that's a pretty typical thing to do, but it doesn't always have to be that way. And there are reasons why you might want to go down or up, but we're not going to talk about it today. But we'll touch on these things as we see examples of this in actual architectures that are being used today. But that's a great question that I'm ignoring until some day in the distant future. Yep, if we want to add a third layer in, we just keep doing these compositions. It actually feels really disappointing. To me it does when I look at that. I'm like, that doesn't look good. That's just like terrible. But that's what we do. Right. You're going to be doing things like this in your homework, implementing multi-layer neural networks. And it turns out that for fully connected networks, this is actually a really, pretty simple thing to do. Tell me, there's one thing in here that you ought to just like, you ought to just be throwing up at right now. Like what's that? Which line? 9. What's wrong with line 9?
It's got the little exponent.
It's got a sigmoid. We were just saying you shouldn't have sigmoids. Well, good catch. If you turn this in, minus 1,000. Anyways, you're going to be doing this very thing in your homework, and it's going to be so much fun because you're going to be like, yes, I know how to do this for 2 layers, and now I want to do this for 1,000, but I'm going to use PyTorch to do that and not my own Fuji code. All right. Good. So there's like the nomenclature here about like how many layers there are. Has to do with basically how many of those W's we're doing. So when there's 1 W, it takes us from the input to the output. That's actually not a neural network, or it's a zero-layer neural network. It's really, depending on the activation function, it's something like a logistic regression or something like that. But as we start to add in, more linear layers in those activations, each one of those beyond that, your first linear layer is giving you additional hidden layers, and we talk about those as the hidden, as like the depth of the network. So 1 hidden layer, 2 hidden layers, 3 hidden layers, and so forth. And that, we're showing the full connectivity here. Every input's connected to every output at a layer. I'm going to skip through this real quick and just point out one thing here at the very end. So back in the 80s, there was this really interesting theorem that was proved. You can read it here, but basically it says, this is proved for sigmoid activation functions, but you can extend this to the family of continuous sigmoid functions. But anyways, the idea is this: a neural network, the family of neural networks with a single hidden layer, is dense in the space of continuous functions. This is actually on a finite interval, so or like a finite volume in higher dimensions. But basically, these things are dense in your set of continuous functions. What does that mean? Any mathematicians here want to bravely tell us what that means, or anybody who knows it? If these functions are, if this set of functions is dense in the set of these continuous functions, what does that mean? Yeah.
Every one of the functions is greater than that.
Close. It's basically, given an appropriate measure of like the distance between functions, it means that for you give me, it's a classical, you give me an epsilon, I can find a neural network with a single hidden layer that will approximate that to within that, that distance epsilon between those functions. Basically, it means I can find a sequence of neural networks that is becoming a better and better and better approximation of my continuous function, and then in the limit, it is becoming that continuous function. So what it means is basically I can get any kind of like any behavior that I want out of like any continuous behavior I want. I can approximate to any to any tolerance. I can approximate as well as I want with a neural network. That's good. That means that neural networks are the thing that we should be looking at. Like they're dense. That's great. Like all we're gonna do now is find the right neural network for our problem, and we're done. And it's only a single hidden layer. There is a problem though. Yeah, there's not every function, but most of our functions that we care about are continuous, or piecewise continuous, which this can be extended to. I'm sorry, the time's up, so I'm just going to skip through all of this and this kind of fun explanation. There's one big problem here. It's exciting result. It's not really an exciting result, and the reason is that the size of this hidden layer here typically has to grow to be huge. It needs to be exponential in the input dimensions to be able to approximate our continuous function well enough. So totally exciting on the one hand, like a nice theoretical result, but bad practically. There's going to be way too many units here. The size of this layer is going to have to be way too big for it to be practical for us to just learn a bunch of single layer neural networks. So what does that mean? Well, it was really exciting, to find this, but we practically couldn't do it. The way that we overcome this these days is with depth. So instead of we basically kind of think of this as factorizing this monster layer into a bunch of smaller layers that follow one after another, and we compose them together. And that allows us, in some sense, to recover this sort of universality. Now, the same theorem doesn't apply for ReLUs because of certain mathematical things that I'm not going to get into today. But the take-home message here is that these neural networks in general do represent a very large class of functions that are useful for learning all kinds of, crazy nonlinear behaviors. In particular, kind of any continuous thing you might want to do, no matter how nonlinear. So that's good, and as we move forward now in the class, we're going to be talking about depth and how we get to larger and larger, to more and more depth in our networks, so that we can do all the cool, crazy things that are being done with neural networks today. Okay, sorry for going 5 minutes over, and I was late to begin with, so I threw everything off today, but I appreciate you sticking around. I'll be here now for however long, having an office hour, so come up and